In the second lecture of Chapter 2, we are going to talk about two things. How do we size CSTRs and PFRs if we are given the rate of disappearance of A of function of conversion? And when we say size, we mean determine the reactor volume. How big must it be to achieve this conversion? And then we're going to determine the conversion for reactors in series, when you might have a CSTR followed by a plug flow or vice versa. And also, this will lead then to show how we arrange our reactors, whether plug flow comes first or a PFR comes first or so on. So last time, we took the mole balances we had from Chapter 1, defined conversion, and then put the mole balances all in terms of conversion. Now we're going to look at how we're going to evaluate these equations, such as the PFR, if we're given the quantity FA0 over RA, if we were given that from experimental data or we did it from theory, that we got that as a function of x. If that's the case, then we can just carry out this integration and we can determine the reactor volume V for a CSTR, PFR, or so on. So how we get this will be discussed in later chapters. For now, we'll just say we obtain it from experimental data. Now, a typical curve might look something like this for an isothermal reaction. And you can see that if we have an isothermal reaction in which it's first order, and we'll learn about that in the next lecture, the rate would look something like this. So as the reaction proceeds and conversion increases, we see that the reactants are used up, and so therefore the rate is going to decrease, so 1 over the rate will then increase. So with regard to a CSTR, our equation was FA0 over minus R evaluated at x1 times x1. So x1 would be this distance here, and FA0 over minus RA at x1, so we go up here, find the intersection here, and that will be FA0 over minus RA at x1. So it's just the area of this rectangle will give us the reactor volume V on a Levenspiel plot. Now let's consider a plug flow reactor. Now in a plug flow, the rate varies continuously down the length of the reactor. Whereas the CSTR, we just said, the rate is that at the exit where x1 is, and that will be at where the rate is the lowest. But here the rate's going to start off high and then decrease to a smaller value as we move down the reactor. So in this case, we have the volumes, the integral from 0 to x1 of FA0 over minus RA dx. Well, that's just the area under the curve of a Levenspiel plot. Now, to get that area, we can do a number of things. Some of them very simple. If you want a quick and dirty way, we could use Simpson's 1/3 rule. We divide the curve into two parts, delta x, and then evaluate the at here, here, and here in the Simpson rule formula, and then we can calculate our reactor volume V. We can also use other techniques such as trapezoidal rule, 3/8 formula, the 5-point quadrature formula. You would use these later ones depending on the steepness of the curve. Now let's talk about reactors in series. You have two reactors. You want to hook them up. So we feed to the first reactor, and that will be FA0. And then we're going to exit the first reactor, and that will be FA1 at point 1. And we're going to feed it then into a second reactor and then come out at point 2. And that will be X2 FA2. Now, we define the conversion at any point up to I as the total moles that have reacted up to that point divided by the moles of A fed to the first reactor. So X2 is all the moles that reacted up to here in reactor 1 plus reactor 2 divided by the feed to the first reactor, which would be just FA0. Now this is valid if there are no side streams. You don't take anything out or put anything in as we go along. Again, the moles of A reacted up to point I, let's say this is point I here, divided by the moles fed to the first reactor. So let's look at an example of this. This is a curve for an exothermic reaction where we have Fa0 over minus Ra. Now the reason it looks like this, because it's exothermic. So as the reaction starts to take off, the temperature rises. As the temperature rises, the rate of reaction increases. So 1 over Ra is going to decrease. But then as the reaction proceeds and the reactants are used up, then we're going to find out that the rate will decrease again, and 1 over Ra will then increase. So this is a typical curve for an exothermic reaction. In fact, this was taken right out of a chapter 12 curve for this. But again, what we're trying to do here is, look, simple means. If you have Fa0 over minus Ra, we can design a lot of things. So let's look at this reactor sequence. A CSTR, a plug flow, and then a CSTR again. This is point 1, point 2, and point 3. So at point 1, we have Fa1, and that will be A0, 1 minus X1. At point 2, Fa2, molar rate exiting here, will be 1 minus X2. And similarly, 3 here, the molar flow rate here will be equal to Fa0, 1 minus X3. Okay, so what we want to do is now size each one of these reactors given that Levenspiel plot I showed you. So for reactor 1, it's just V1 as before. And so for reactor 1, we've already done this twice before. It's just Fa0 times X1 divided by the rate of reaction in the reactor at point 1. On a Levenspiel plot, it looks something like this. A little bit different because at X1, we have to evaluate this quantity at X1. So we just at X1, we have this quantity as one side of our rectangle. And then to get the height, you come over here, add X1, and find out what Fa0 over minus Ra is at X1. And we see then this is going to be the area under the curve. Will give us our CSTR volume. Now, for our PFR, we're going from X1 to X2. So we start out with our equation, dx dV is equal to minus Ra over our molar flow rate entering. But the limits of this integration are, we're going from when V equals 0, say, then X equals X1. When V equals the volume V2, then the volume is equal to V2 at X equals X2. So we're going to be integrating from point 1 to point 2, and that'll be integrating from X1 to X2 of Fa0 over minus Ra. On a Levenspiel plot, it looks something like this. It would be the area under the curve between X1 and X2 to give us our reactor volume V2. And then finally, we look at our last CSTR. We're coming in here at Fa2 is our entering, leaving is Fa3. So our mole balance is in Fa2 minus out, Fa3 plus rate of generation is the rate of reaction in reactor 3 times volume V3. Well, we just saw Fa2 is just this quantity here. Fa3 is Fa0 minus Fa0x3, and this then is our generation term from here. Rearranging and dividing by minus Ra3, we see this is the volume of a CSTR necessary to increase the conversion from X2 at point 2 to X3 at point 3. In terms of our Levenspiel plot, it'll look something like this. This being X3, and this being X2. So it'll be this distance here, the the base will be x2 minus, or x3 minus x2, times the height. Well, we have to come up here. At x3, we have to find out what is FA0 over minus RA at point 3. Well, we simply come up here, and we would then read off the graph here of FA0 over minus RA, and that would be the height. So we have the base times the height, and that will give us our reactor volume V3. So, summing up here, we had 3 reactors in series, and we were able to size each of one of them using a Levenspiel plot. And for the real data, we've taken from Chapter 6, this is something what it'll look like. The volume of the first CSTR is 188 decimeters cubed. The volume of the plug flow reactors is 380 decimeters cubed. And the last CSTR is 100 decimeter cubed, necessary in the conversion from 0.6 to above 0.64. So that essentially is the end of lecture 2. But I'd like to point out one more thing in terms of a definition. And that is the space-time tau. Now, this is a reactor volume of 0.2 meters. If we go upstream 0.2 meters, the space-time is to put an equivalent volume of fluid inside the reactor. So the space-time is the time necessary to flow this volume completely into the reactor. So it's the volume of fluid divided by the volumetric flow rate, and that will be the space-time. And that ends Chapter 2, Lecture 2. And next time, then Dan will look at Chapter 3, where we start the second building block of our tower to study chemical reaction engineering, and that is rate laws.